Welcome back. We were talking about multiple access system via satellite, and already we have covered that very common frequency division multiple access FDMA, and then we continued our discussion on time division multiple access TDMA via satellite, and in that we were trying to see how the burst from the individual station reaches in proper time at the satellite with respect to the reference burst of the TDMA frame, and then we receive that burst, and what is the characteristics of burst, how do we receive that. We discussed about the beginning of the burst. There is a unique word, how to detect the unique word. If there is an error, what is the probability of misdetection and probability of false detection. Those estimates we have just seen. So we will go back to this synchronization of this TDMA burst on the satellite transponder. Let us look at this slightly older slide. This we were estimating that when to transmit, that was the unknown factor D we were trying to find out. Now we have calculated, and based on the estimation of integer number m, we calculated and found out what is the D, and a time slot t is already known with respect to the reference burst. So we transmit with respect to this. Now that is only the transmission. It has been properly transmitted or not, our estimate of D is correct or not for that particular station, we will come to know after this burst reaches the satellite, and then from the satellite it is broadcast down. So we will be receiving the same burst. So we will come to know after reception of that whether this time t with respect to the beginning of the reference burst and start of the burst, what this particular station has transmitted, this t has been properly maintained or not. Now that means we are transmitting and receiving back, and if it is not properly maintained, we slightly adjust it, we will advance it in terms of time or retard it in terms of time for the next time transmission with respect to the reference burst reception, that is another D, and we will be transmitting that. Now this is forming a closed loop. So this is called closed loop synchronization. It takes some time or some number of frames which is multiple of the propagation time up and down, as well as some estimated time of D. So that it will take to properly place the burst in the right place in the frame. So the total user data in the beginning of this synchronization is not sent, only a preamble is sent somewhere giving some gap of few bytes both sides, so that you don't by mistake you don't fall into the previous burst time. That means previous station's time, your allotment time. So sometimes it is transmitted at the middle of the allotted burst and the drift is calculated, and slowly it is drifted out. So this closed loop synchronization takes some time, but there is no way we have to know what is the burst clock. We have to find out the burst clock. So for that this is referenced. But sometimes the stable clocks are available, and if the bursts sizes are clearly known, using that stable clock we can do it. So let us go forward, and this is called open loop synchronization. If the slot timing can be supplied to all station by an independent system like GPS. GPS, in addition to position, it can give a time also, which is very precise. It is stability is very high, because the GPS satellites are carrying the atomic clock. So with the high stability, and all the stations are receiving the same clock from the satellite. So therefore all of the stations are synchronized with respect to the GPS clock. So that means the whole network is synchronized with respect to GPS clock. If we can do that way, then the burst clock timing adjustment you don't have to worry. In that case, reference burst unique detection is not needed to find out the slot clock generation time, but you still have to know the phase, you still have to know where the reference bus is, and with respect to that you have to transmit, and you need to know the ranging information, that is the propagation time p for uplink and downlink. So, with some additional information you can manage with a open loop synchronization. So, in that case it will be much faster to start transmitting actual data. In closed loop synchronization you have to synchronize, it will take a couple of propagation time and frames, whereas in this case of open loop synchronization it is much faster, but it all depends on the slot timing by the independent system, how stable it is. Of course, GPS is quite stable. Now, let us who are using it and what is the problem, let us see. Like FDMA, the frequency slots are allotted there, here time slots are allotted to each individual station. Now, if you are not having a continuous traffic from that station, so those time slots will be wasted. Just like in FDMA we have said that if it is a non-continuous traffic, the bandwidth is wasted, here the time is wasted. And obviously, let us see like VSAT operation using our automatic teller machine, that is the ATM in the bank. In that you have a traffic which is bursty. Sometimes the ATM is empty, nobody is transmitting, and sometimes some queue is there, people are transmitting for a couple of minutes. So, therefore, in these type of VSAT network, if it is operating in TDMA, for each VSAT, if it is the time slots are allotted pre-assigned and allotted permanently, there will be underutilization. So, now what is done is these slot VSATs, they ask the central station that you give me a time slot, and central station, based on the availability of time slots, they allot that time slot. So, it is a demand assigned type of time division multiple access. It is called demand assigned TDMA. So, you ask for it and you get it. So, that means more number of VSATs can be brought into the network, assuming that all VSATs are not simultaneously on, or not simultaneously asking. They are on, but they are not asking for the time slot, their traffic is not continuous. In those cases, the demand assigned TDMA. Where the traffic is continuous, then of course the pre-assigned TDMA is the best solution for that. Now, let us do a transponder utilization calculation. That is based on the first you can calculate what is the transmission bit rate. Transmission bit rate and information bit rates are different. We have seen that efficiency calculation in TDMA. Information bit rate is actually the useful bit rate, I should say. Useful bit rate is excluding the overhead bits, and transmission bit rate is at the rate each bit is transmitted. So, TDMA transmission bit rate can be found from the power estimate. We remember this expression, that is C by N naught is EIRP plus G by T minus losses minus K, and C by N naught is EB by N naught plus R. So, keeping the bit rate R in the left hand side, we bring the EB by N naught on the right hand side. So, in dB the expression becomes the transmission bit rate is equal to EIRP from the satellite minus the downlink losses, and G by T of the receive station minus the Boltzmann constant minus EB by N naught. But this actual information rate, which is I should say useful bit rate or actual information bit rate, is much less because overhead bits are there. So, if we call it Ri, so Ri is some efficiency time the transmission bit rate. So, let us call this efficiency eta f. So, number of voice channel, if the RV, if we say voice channel bit rate, so it becomes the Ri by RV, that is eta f into transmission bit rate by RV, where eta is the frame efficiency, eta f is the frame efficiency, and RV is the voice channel bit rate. So, if we have all these parameters available with us, EIRP, losses, G by T, etc., and if we know that the efficiency, that is the useful bits how many they are, or overhead bits how many they are, So, from the transmission bit rate we can find out the information bit rate or useful bit rate and voice channel, assuming all of them are using voice communication and at a constant bit rate each of them, then that is the number of voice channels that can be supported. So, number of voice channels can be found out from the bandwidth, that is from the power. From the bandwidth also you can find out number of voice channels. Let us see how it is. Transmission bit rate is total TDMA transmission bit rate is the transponder bandwidth. I assume the full transponder is being used. So, transponder bandwidth multiplied by the spectral efficiency, the type of modulation what you used, that is how many bits per hertz is being used, that multiplied by the bandwidth and divided by the filter rule off. The whole transponder bandwidth, even if you use, will use a filter, because the spurious thing should not fall into adjacent channel. So, there will be filter and there is a definitely filter roll off factor. So, 1 plus R. So, transmission bit rate R is equal to transponder bandwidth B into eta S. Now, eta S is spectral efficiency for the modulation divided by 1 plus R. And then information bit rate, as we have seen earlier, is eta F time, that is frame efficiency time, the transmission bit rate, which you have just now got in terms of bandwidth, from the bandwidth and filter roll off and the type of modulation that is used. And then we can find out the number of voice channels, that is Ri by Rv is eta F into R, and R is eta S into B divided by 1 plus R, and Rv is already there in the denominator. So, by knowing the frame efficiency and the spectral efficiency and the bandwidth that is available and the filter roll off and the bit rate of the voice channel, we can find out the number of voice channels that can be supported, assuming all voice channels are transmitting at the same rate. So, that is earlier expression was in terms of power. From the power we can find out, and here we can find out from the bandwidth. Let us take some example, as we have done earlier. Let us take small examples so that we can get into familiar with the numbers. And as I always say that it's better to just don't copy or calculate on the numbers, try to understand the meaning of this number, so that implications will be much more clear. You will enjoy the satellite communication. Find TDMA transmission rate capacity for a 4 gigahertz downlink with a satellite EIRP of 22.5 dBW. Downlink path loss is 197 dB. You just, as I just now said, that if you just don't take this number as it is, but look at the meaning of this number, 197 dB and 4 gigahertz downlink. You remember the path loss calculation, that is in terms of lambda and the distance. Roughly the distance will be more than 36,000 kilometer here. You can calculate that. So, 4 gigahertz generally we get 197 dB at the downlink, and the received G by T of 30 dB K, again 30 dB per K. Received G by T is a larger station, G is very high, that is why you got 30. We have seen similar numbers earlier in FDMA examples. EB band not required for the required BER is 8.5 dB. Here I didn't specify the BER, for a particular BER it is 8.5 dB. It depends on what type of modulation is being used, and there is a link margin in the downlink, 5 dB link margin is provided. Now, let us go back to the calculation. C by N naught is EB by N naught plus R, that is transmission bit rate, in dB, or multiplied by R in ratio if C by N naught is in ratio. Now, and C by N naught is equal to EIRP from the satellite, G by T of the station, receive station, minus the losses, downlink loss and miscellaneous loss, anything, and then the Boltzmann constant, and if there is a link margin also has to be added. Then the transmission bit rate EIR, C by N naught is replaced by EB by N naught and R, and EB by N naught is taken in the right hand side. So, the transmission bit rate is equal to EIRP plus G by T minus losses minus K and minus EB by N naught. These are all in dB. I put these numbers, so the transmission bit rate comes out to be 70.6 dB hertz. You remember the K number, that was minus 228.6. So here minus minus becomes plus. All other numbers are already available in the problem. So R comes out to be 70.6 dB hertz, and convert into ratio you will get 11.48 megabits per second. So we have been asked to find out transmission capacity based on or transmission rate based on EIRP and G by T, and we have calculated based on C by N naught. Let us take one more example, which is find the TDMA transmission rate or transmission capacity for a full transponder bandwidth. This is a bandwidth example. For a full transponder bandwidth of 72 megahertz, QPSK modulation, filter roll-off factor 20% of the bandwidth, and find the useful bit rate for frame efficiency of 95%. Just look at this number, 72 megahertz. Normally we were always talking about 36 megahertz transponder. This is a much larger transponder. Some cases, normally most of the satellites they use 36 megahertz, but in some cases where larger bandwidth or larger bit rate communication is going on, then Intelsat and some of the satellites support such a wide band transponder, 72 megahertz. Okay. Now here the calculation is straightforward. That is that spectral efficiency is 2 because it is QPSK modulation, that is 2 bits per hertz, and then 72 megahertz, and filter roll-off is that is 0.2, and 1 plus R is 1.2. You get transmission rate of 120 megabits per second, and frame efficiency is given 95%. So you can find out what is the information bit rate or useful bit rate, that is 114 megabits per second. There is one more, that is find the number of voice channels. In this case trying to calculate the capacity in terms of voice channel. Earlier we calculated only the useful bit rates. For a TDM link with C by N naught 85.5 dB hertz, EB by N naught of 8.5 dB, and TDMA frame efficiency is 85%. Quite poor. Normally it is more than 90%, and voice channel rate is 64 kilobits per second. So the TDMA transmission rate, transmission bit rate is C by N naught minus EB by N naught, and that becomes 77 dB, which is so many bits per second. It is more than 50 megabits per second. And the useful bit rate, since the efficiency is given, frame efficiency into TDMA transmission rate, so you multiply these numbers and you get the useful bit rates of 42 megabits per second. Here it's more than 50 megabits per second, is more than 42 megabits per second. Because of the frame efficiency is quite low, 85%, and this number is quite a large difference. Now we have to find out the number of voice channel rate is 64 kilobit. Since we have got the useful bit rate, this divided by the voice channel rate, that is useful bit rate by voice channel rate, you get the number of voice channel. Divide this, you get 665.393 as the number, and again we have to take the lower number as the integer, that is 665. You cannot take the next higher integer. We have discussed this logic earlier. So this is how some of the small quick examples are given, very simple calculation, but you have to know how to approach to this. There is one more advanced level TDMA being used for very high traffic network, and quite an advanced level of switches are required, which is called satellite switched TDMA. It is used by Intelsat in some of the Intelsat satellites. If the multiple antenna beams, it is with multiple antenna beams, and each antenna beam is covering at different regions, and if those switching of the antenna beam can be done very fast, of the order of megabits and hundreds of megabits, it's quite a fast switching, then additional level of access capability can be added, and the number of users can be enhanced or increased, because more number of users can be supported, because you are switching between beams. And to do this, there is no need for onboard regeneration. Here your signal is only RF signal are redirected from one beam to another beam, one coverage area to another coverage area at any instant of time. Since they are being switched in terms of time, so the RF signal, or at the bring back at the IF level and switch. That is enough. So switch at the RF or IF level is enough. You don't have to come down to regenerating the bits and then redirecting, that is demodulation and modulation is not required. In transparent transponder, therefore onboard transponders are not used in this case. The transparent transponder, bent pipe transponders, it can be achieved with a n by m matrix at RF or at IF. The switching has to be done in the synchronism of TDMA frame, because each switch will hold for some time, which is equivalent to TDMA frame. So the switch has to be properly synchronized. This is the tough thing. One is switch has to be very fast switching. That is possible using microwave switches, but then it has to be synchronized with the TDMA frame. That is a interesting issue. Anyway, we won't go into circuit details. We are just talking about the systems. So let us see the SSTDMA. There is a quick example I am trying to give. There is number of switches. Let us say there are 3 beams to be switched. So how many number of switches? That is 3 into 2. That is 6 number of switches are required. Let us say west, central, and east. In a say, let's say India. India is covered with 3 beams: west, central, and east. I assume the northern and southern are covered partially by west, central, and east beams. 3 beams scenario for easy example. And so in the first switch mode, in a configuration, the switch will be connecting to west beam to central beam, central beam to west beam. See, it's making a full duplex, and east beam to east beam, and then full duplex. This in the second mode, west beam to east beam, center to center, east to west. So like that, different combination. You can draw the picture. You can see different combinations are there, and it will come back to the first switch mode. So like that, 6 switching modes will be required, and then it will come to the first mode, and it will repeat on that. So all this quick discussion on TDMA, certain issues came up, that is, it needs high transmission rate. Though there is a big advantage of TDMA at the beginning we stated, and it's clear that at a time one carrier is coming up and occupying the full resource, taking the full resource in terms of bandwidth and power. And even if the transponder is nonlinear, you can operate at the saturation point, so you can extract maximum power from the transponder. So URP saturation will be operating. Therefore you can cover to the largest possible extent, or your G by T of the user can be reduced because your transmission EIRP is high. Either coverage can be larger or G by T can be reduced. That is the biggest advantage of TDM. But the price you pay for that is that whatever continuous data is coming, you have to compress them and transmit, so that within 1 bit time you should be able to complete the all transmissions and come back to the first user, so that you can take up the next bit. So therefore it has to be compressed, and that means high transmission rate. Meaning of high transmission rate is the R is high, so therefore your C will become high. Requirement of C by N naught will be higher. So EIRP obviously will be higher, or G by T has to be higher. The second issue, this needs a high power transmission. So second issue is the synchronization. All stations, they may be geographically far away, and the clock of them which is running between them is to be properly synchronized in terms of burst clock. At the satellite, they should reach in their allotted burst time properly. So you need some sort of a reference station who supplies the frame timing, and obviously from the frame timing, repetition of the frame and knowing the size of the burst, you can extract the burst timing. So burst time clock has to be extracted by a common station which will be transmitting this. So common station's clock will be synchronized by all the receiver, will be synchronized to all the receiver clocks. So that way the receiver clock's burst clock, I should say, burst clock gets synchronized. It's different than your bit clock or frequency. That is different. This is the burst clock. will be synchronized. And we said that this is, of course, you have to pay for a reference station, and since one reference station, if it fails, the whole network fails. So therefore you need 2 reference stations, so cost goes up. And not only that, you have to send the reference burst, which will be part of the TDMA frame. So that is a overhead of TDMA frame. So efficiencies you are losing in terms of guard time and the reference frame time. So that's the synchronization loss. And the other more difficult, which is not a part of this course, is the demodulation has to be bursty demodulator. That means there are a guard time when there is no transmission. A receiver is receiving some blank time, that is no transmission, and suddenly a burst appears, which has all the frequency, clocks, beats, etc. So your demodulator has to quickly lock into it. That lock-in time is very important, and for that the training sequence which is given, that is carrier recovery time, is given to recover the carrier. Bit timing recovery time is given to recover the bit clock. So the burst demodulator is also another new additional load into the total system. So these are the couple of issues in TDMA. So we stop discussion on the TDMA here, and we'll continue our multiple access discussion in the next period. Thank you.